Hello everybody, welcome to Calculus 1 online at Frederick Community College. My name is Professor Lachman. I will be your instructor for this class, and I would like to welcome you all to the very beginning of our study of calculus. In this lecture, we will begin a very important concept, and that is the limit of a function. The plan for today's lecture is to start with an intuitive definition of a limit. Then we will proceed with a formal definition and an introduction of one-sided limits. And we will finish our lecture with a discussion of infinite limits. So this is just a brief outline of what is to come. Before we do all of that, let me go ahead and give you a brief summary of what we've done in our previous math classes, and that is the study of properties of functions, all sorts of various functions. And here on the right side of this slide, you see a graph of what looks like a quadratic function. Okay, so a graph that you should be fairly familiar with. Let me go ahead and give you the equation that corresponds to this particular graph. So that would be y is equal to x squared plus 1. You can see that this parabola is shifted 1 unit up along the vertical axis, and that's represented by plus 1 in the equation. So for functions, when we discussed their properties, we talked about things like domain. Okay, so the domain of a function is all values of x that we can plug in into the equation. And for this particular function, the domain is all real numbers, right? So that would be all of the x values on the horizontal axis. We talked about things like range as well. So range, okay, would be all y values. And for this particular function, that would be what? All y that are greater than or equal to 1. Okay. We've also discussed things of this nature like function being increasing, decreasing, obtaining maximum or minimum value, and so forth. So I'm just giving you a very, very brief reminder of what we've done in our previous math classes and what the expectation is that you are comfortable applying these properties and using them when appropriate. Okay, so at some point you might need to review some of these properties for functions that are a little bit more complicated, such as trig functions, exponential, and logarithmic. Now let me go ahead and introduce the 3 functions that I'm going to use as motivating examples to start our discussion of limits. You will see that these functions will also be used in later portions of today's lecture. First, let's take a look at this graph right here. We have a function that looks like a linear function that's undefined for 1 point. So for x is equal to 3, we see that we have a hollow dot, and that means the function is undefined for that particular value of x. Let's go ahead and give this function a name. So let's say this is going to be f of x. All right, so because we have a hollow dot on the graph, that means f is undefined for x is equal to 3. Having said that, we can still discuss the behavior of this function around x is equal to 3. So what do I mean by that? Let's say we're moving along the x-axis and we're approaching x is equal to 3. We're approaching it from the left side. Okay, so this is where we're coming from. What happens to the graph of the function? Okay, well, you can see that our function is approaching the value y is equal to 6. Okay, and similarly, as we move along the x-axis from the right. So we're approaching x is equal to 3 from the right side. Let me go ahead and indicate that by these arrows right here. What is our graph doing? The graph of our function gets closer and closer to y is equal to 6. Okay, so we can say that as x approaches 3, how does our function behave? F approaches 6. Okay, and that's your intuitive notion of a limit of a function. Okay, all it is just how your function is behaving around a certain point. Okay, so let's take a look at the next example. Here I have another function that looks like a rational function. Let's go ahead and give it a name. So let's say this is going to be g of x, and this function is undefined for x is equal to -2. Okay, as we know from our previous classes, rational functions can have asymptotes, right? Okay, so x is equal to -2. This is where we have a vertical asymptote. And what happens to our function as we get closer and closer to -2? Well, let's take a look at it. Okay, as we approach -2 from the left side, the branch, what does it do? So that would be the left branch of the graph. It goes up to infinity. Okay, so that's how we indicate that growth. It grows very, very high and goes all the way to positive infinity. Okay, what kind of behavior do we have as we approach x from the right? Okay, similar, right? So as we approach x is equal to -2 from the right side, what happens to the right branch? The right branch is also going to positive infinity. Okay, so now you can have this informal notation saying g of x goes to positive infinity as we approach x is equal to -2 from either side, right? So let me go ahead and mark it here as we approach x either from the left or from the right. The function g behaves the same. It goes all the way up to infinity. Okay, so in the first example, we had a behavior of a function so that it was going to a finite number. And in the second example, that's where the two branches go into positive infinity. Let's take a look at one more example. So here is our last example for this slide. We have a function that's piecewise defined. Let's go ahead and give it a name. So h of x over here, okay? And it is defined for all values of x, except we have a jump at x is equal to 2. So that's going to be our point of interest, okay? So notice that this particular function is defined at x is equal to 2, and it's going to be this point right here. We can go ahead and make a note that h evaluated at 2 is 6. Okay, so if you look at the graph, that would be the solid dot. That's the value that you're going to pick. Okay, now the behavior around this point, as you can already predict, is going to be different depending on which side we're coming from. So if we're coming from the left side, okay, so we're coming here on the left, okay, we're approaching x is equal to 2 from the left side. What happens to the function? Well, this is an increasing function. It's a linear function, and it is increasing up to this point, and it obtains this value here, right? So h is going to 6. Now notice that if we switch the side and say, now let's go ahead and approach our x from the right side. What happens now? Now our function approaching a different value, and it is approaching 3. Okay, so here's your first example of what can happen to a function when it's approaching different values. All right, but the main point of these examples is just to show you that limits, it's just the behavior. Think about limits as behavior of a function around a particular value of x. Now let's go ahead and take a look at an example where we're further exploring the idea of limits using a table. We're going to work with the function f of x is equal to square root of x minus 2 over x minus 4. And we would like to discuss the behavior of this function around x is equal to 4. So let's go ahead and take a look at the following table. Here on the left column represents values of x such that we start with 3.9, which is to the left of 4, and we are increasing the values of x, approaching x is equal to 4 from the left. So pictorially, that would look something like this. Let's say this is our real line. Okay, and 4 is somewhere around here, and let's say 3.9 is over here, and then we increase it to 3.99, 3.999, and so forth. So we are approaching 4 from the left side. Okay, now as you can see, I am using Desmos to construct this table. Once you plug in your equation for x, okay, so f of x is equal to square root of x minus 2 over x minus 4. These values are computed automatically, and of course you can just use your calculator to confirm these values. Now what happens to our function? Well, we start with this value right here, 0.2515823. Okay, and then this is slowly but surely approaching what it looks like a quarter, right? So 0.25. All right, we can make a conjecture that as we are approaching x is equal to 4 from the left, the behavior of the function is what? F of x is going to 1/4. Okay, and that is based on this table right here. Now let's take a look at what this function looks like as we're approaching 4 from the right side. Okay, what would that look like? So now I'm going to start at 4.1. So let's say somewhere over here. And now I am decreasing the values of x. Okay, for 4.1, the value for f turns out to be 0.2484567.3. Okay, and as we are decreasing the value of x and we're approaching 4 from the right, okay, so we're going to 4 over here for x. Okay, so that would look like what? So on your real line, we're approaching this value right here. What happens to the function? The function goes to 1/4, right? So 0.2499998, that is basically 1/4. Okay, so this is a similar idea that we've discussed on our previous slide, but now numerically we can confirm that what happens to our function from either side, whether we're approaching from right or left, the value of the function goes to 1/4. And then if you graph this particular function, this is what we're going to get, okay? That confirms our result. So this portion right here, the left branch, that corresponds to what? So that corresponds to this table right here, and then the right branch of this graph that corresponds to the second table, okay? And now we can introduce a formal notation for this particular concept. Oops, let me go ahead and erase this arrow right here. So this would say what? What is our conclusion? We would say as x goes to 4 from either side, okay, so limit the behavior of the function as x goes to 4 from either side is equal to 1/4. Okay, so this is your first introduction to a formal notation of a limit of a function. Let's take a look at another example where we're exploring limits using tables, and this time our function will involve a trigonometric expression. So we're working with the function f of x is equal to sine of x over x, and we would like to discuss the behavior of this function around x is equal to 0. So we're going to have the following picture. Okay, so we have 0 somewhere over here, and we would like to see what happens to our function as we approach 0 from the left side, and then also what happens to f as we approach 0 from the right side. Okay, let's take a look at the first table. So this table represents the behavior of the function as we approach 0 from the left. Okay, so let's say we start with negative 0.1, so maybe somewhere over here, negative 0.1, and then we increase our values, okay, as we approach 0 from the left. What happens to the function? So if you were to plug this into your calculator, okay, and make sure that your mode is set to radians, you're going to get the following values. Okay, so looks like our function is approaching 1. Okay, so as x gets closer and closer to 0 from the left side, the function's value go to 1. Okay, now what happens to this function as we approach 0 from the right side? Here is a similar table, except now our values are positive. So we also start at 0.1. Okay, so somewhere over here, and now we're decreasing the values as we are approaching 0 from the right side. What happens to our function? Well, you notice that we have a complete symmetry here. The values are exactly the same. Okay, so the values of f also go to 1. So we can make a conjecture here that as we approach 0 from either side, the value of the function approaches 1. Okay, and if you were to graph this function, this is what it's going to look like. All right, so we have 1 over here as our limit, right? The behavior of our function. This is where the function is convergent to from either side. Now notice that the function itself is still undefined at x is equal to 0. So there is a hole in that graph, okay? But that doesn't mean that we can't discuss the behavior of this function around x is equal to 0, and we can. We see that both these branches, left and right, approach 1. Okay, so let me demonstrate it. All right, as we're coming from the left, we go to 1. As we're coming from the right, we also go to 1. So what would our conclusion be for this particular example? The conclusion is what? The limit of this function, that's the behavior of this function, as x goes to 0, and when we write it like this, x goes to 0, x goes to a very specific number, we mean that from either side, x goes to 0 from either side, we have the same behavior. We're going to 1, okay? So that is the formal notation to represent the behavior of this function around a particular point x. In this case, x is equal to 0. Now that we have seen several examples of functions and discussed their behavior around a particular point, this is a good time to introduce the formal definition of a limit and discuss the notation that we will be using throughout the class. Now here you see the definition provided by our course textbook. You do not need to memorize this. We just need to understand and have this intuitive notion of what a limit is. So we say as x approaches a, some number, a in this case is just number, if f of x gets closer and closer to another number L, then we say the limit of this function is L. That's all that it's saying. Okay, and you have seen this notation already for a couple of examples that we've discussed previously. So now let's go ahead and take a look at one of the examples that we started our lecture with. Okay, so this function right here, it's a linear function that's not defined for x is equal to 3. However, we've talked about it and we said, well, as we approach 3 from the left or from the right, the value of the function gets closer and closer to 6. So how would we use our notation for this particular problem? We would say that the limit as x goes to 3 of our function f of x, and if you recall, we did name this function f of x, is equal to 6. Okay, now notice I want to emphasize the following fact that f of 3 is undefined. Okay, because we have that hole in the graph, we say that the function is not defined at that particular value of x. But that doesn't mean that we can't have a limit. The limit does exist, and the limit in this case is equal to 6. Let's take a look at the formal definition and notation for one-sided limits. Once again, you see the definition from our course textbook. You don't need to memorize this whole thing. We just need to understand the basic idea of one-sided limits and use proper notation. So this is something that we've discussed already at the beginning of the class when we talked about the behavior of the function as we approach x from either side. So now let's talk about the notation. We say that limit from the left, okay, would be denoted like this. X goes to a, and we put negative in the power for a. Okay, and that is how we identify that we are looking at the left limit. Okay, what happens to our function? How does it behave as we approach a from the left side? So that's going to be the notation that we will use for limit from the left. All right, now what about limit from the right? Very similar. If we would like to demonstrate the behavior of our function as x goes to a from the right, then we say x goes to a and plus into the power for a. Okay, so that represents the limit from the right. And now let's take a look at our example that we've discussed at the beginning of the lecture. So if you recall, we named this function h. okay? And we said that as x approaches 2 from the left, our function h goes to 6, okay? And then as h approaches 2 from the right, our function h goes to a different value, okay? Goes to 3 over here, okay? So this is a nice example to demonstrate that we have a problem where the two one-sided limits are different, okay? So what is the formal notation for this? Here is how you would write this. We say limit as x goes to 2 from the left, and that is identified by that negative sign, that is equal to 6. And then a limit of h of x as x goes to 2 from the right side, that is something different, okay? That's 3. There is nothing wrong with this, okay? So 6 and 3 are not the same, and that is absolutely not a problem, okay? That can happen, all right? So the two one-sided limits, they do not have to be the same. Now that we have seen this new notation, let's go ahead and take a look at a quick example. So we would like to determine one-sided limits from a graph. And here is a graph of a piecewise defined function. And we would like to take a look at the limits as we approach 2 from either side. Okay, so let's take a look at what they are. So the limit of our function f of x as x approaches 2 from the left side. What would that look like from the graph? So this would be the left branch right here. As we approach 2 from the left side, what does it look like we're approaching for the y? So that is 3. Okay, so the limit will be 3. Okay, now what happens on the right? So as x approaches 2 from the right side, we have a different type of behavior. Okay, we get closer and closer. What it looks like, let's say 0.6, roughly, right? This is approximation. So 0.6, oh, negative. It's negative 0.6. All right, and that would be this value right here on the y-axis. Okay, so notice that the function is defined for x is equal to 2. Okay, so for x is equal to 2, we would take a look at this point right here, and we would say f evaluated at 2 is equal to 3. The left limit is also equal to 3, but the right limit is not. Okay, the right limit is negative 0.6. Okay, and again, there's nothing wrong with this. Okay, there's absolutely nothing wrong with two one-sided limits having different values. At this point of the lecture, I would like to make a connection between one-sided and two-sided limits. And I'm sure you already had an intuition about it. So let's see if your intuition was right. We say that the limit of f of x as x goes to a is some number L if and only if the left limit and the right limit are the same. Okay, and we have seen an example where we had the two one-sided limits and they were the same value. Okay, so here is the example that I'm referring to. We have this line where we have one point where the function is undefined, so that is x is equal to 3. However, as we approach 3 from either side, so left or right, we are approaching the same value of y, okay, and that would be 6. So we already mentioned that the two one-sided limits both were equal to 6, which means we can say limit as x goes to 3 of f of x is equal to 6. Okay, so notice I do not need to indicate the direction. Okay, that's kind of part of the definition that implies that both left and right limits are also equal to 6. Now let's take a look at this other example. So this is our function h, where the two one-sided limits were different. Okay, so what do we say about the limit as x goes to 2 of a function where the left limit and the right limit are different? We would say this limit does not exist, and you can abbreviate it as DNE. Okay, the limit of h of x as x goes to positive 2 does not exist. Why? It doesn't exist because the two one-sided limits are different. Okay, one was 6, the other one was 3. All right, so that is your connection between one-sided and two-sided limits. Now let's have a brief discussion of infinite limits. This is a concept that we will thoroughly discuss in this class, but for today's lecture, we're just going to have a very gentle introduction with a couple of examples, and we'll discuss the notation. So let's take a look at the graph of the following function. We have a rational function that has an asymptote at x is equal to 3, and that's demonstrated by this vertical line. X is equal to 3 is a point that's not in the domain of this function. That is where the function is undefined. Having said that, we can still talk about the behavior of our function around 3. Okay, so what is the limit as x goes to 3 from the left? So this is us going in this direction here, approaching 3 from the left. We can see that our left branch is going down, and we have asymptotic behavior here, so the branch gets closer and closer to this vertical line, but it never touches it. So notation wise, we would say the left limit, so as x goes to 3 from the left of our function f, is negative infinity. Now this is not a number, right? There's no such number as negative infinity. This is just saying something about the behavior of the function. The negative infinity represents the branch that's going down, and infinitely down, down, down it goes. Okay, what about the right side? So as we approach 3 from the right side, what happens to our graph? Okay, it goes up. It gets closer and closer to the vertical line x is equal to 3, but it never touches it. It just goes way up, and that is represented by the following notation. We say the right limit, so the limit of f of x as x goes to 3 from the right, hence that positive, okay, that plus sign is positive infinity. Okay, so again, infinity is not a number. This is just a way for us to identify the behavior of our function. Okay, so that is your first example of infinite limits. So when we say infinite limits, okay, what does that mean? That means y goes to either positive or negative infinity, right? So infinite limits. Okay, so y or f of x, right? So f of x or g of x, whatever we label our function as, okay? But in essence, this would be the y values, either going to positive infinity or negative infinity, okay? Just to represent the direction, okay? Either up or down, All right, so that's our first example. Let's take a look at our second example. Here we also have a rational function. In this case, we have an asymptote at x is equal to -4. Okay, but for this particular function, the branches behave exactly the same. Okay, as we approach x from the left, as we approach -4 from the left, okay, what happens to the branch? Well, the branch goes up to infinity, and that is represented by this expression right here. So limit as x goes to -4 from the left of our function g of x is positive infinity. Again, that's not a number. This is just telling us how the function is behaving. What happens to this function as we're approaching -4 from the right? Okay, same idea. The branch goes up to infinity, and that is represented by this notation here. So we write limit as x goes to -4 plus, that's representing the direction from the right, is also positive infinity. Okay, so here's your first introduction to infinite limits, and as I mentioned earlier, we will discuss this concept thoroughly. Let's finish our discussion with a fairly involved example that will give you a pretty good idea of what you could expect on major assessments such as exams and quizzes. So here you see a graph of a piecewise defined function, and I would like to answer a series of questions about it. We're going to start with f evaluated at -8. I'm going to find -8 on the x-axis, project it, and work with the solid dot that represents the value of the function at that x equal to -8. And if I project it onto the y-axis, we get -3. So f evaluated at -8 is equal to -3. Okay, let's take a look at the limit of our function as x goes to -8, which means we need to consider both left and right limits. So as we go to -8 from the left side, it looks like our limit is -6. And similarly, as we go to -8 from the right, the limit is also -6. So the two one-sided limits are the same, which means limit as x goes to -8 is -6. Okay, now let's switch our focus to the next point of interest, and that is -2. Okay, what happens as we approach -2 from the left? Well, this is the branch that represents that behavior, and it looks like we are approaching 3. Okay, so that's the limit, that's the left limit of f of x as x goes to -2 from the left. Okay, now for the right branch, let me go ahead and make it a little bit clear that this should have an arrow representing that this branch goes all the way up to infinity. So as x goes to -2 from the right, we have different type of behavior. This is infinity. Okay, and since these two one-sided limits are not the same, then the answer for the following question is that it does not exist, right? Okay, so this limit does not exist. Notice that there's no indication here, no minus or plus, so that means we should consider both one-sided limits that are not equal, so we can say that the limit as x goes to -2 of f of x does not exist. Okay, so now we only have two other points to consider. What is f of 6? So let's switch our focus here. F of 6, what is it? That would be this solid dot right here. Okay, f of 6 is equal to 5. Okay, and then it's asking us what is the limit as x goes to 6. Well, notice that as we approach 6 from the left, we get one limit, but as we approach 6 from the right, we get a very different limit. Okay, so the left limit is equal to 2. The right limit is equal to 5. That means limit as x goes to 6 of this function does not exist. Okay, and the last question, this one just asking us what is the limit as x goes to 10 of our function. Okay, so here you would consider the left limit and the right limit. And in this case, everything is good. The two limits are the same. Okay, then we say the limit of f of x as x goes to 10 is equal to 0. Okay, so this should give you a good idea of what we've learned today. So one-sided limits, two-sided limits, okay, how to find them from the graph, and also it should give you an example of what a problem or two might look like on an exam. All right, thank you for watching, and I will talk to you next time.